Hello, my name's Rob Hislop, and of course we're at the Analytics, Big Data and the Cloud, or Big Data and the Cloud conference taking place at Fantasyland Hotel, and we've got one of the guest speakers here, Dr. Thomas Mueller. You're with the University of Alberta.
Yeah, that's good.
Thanks very much for joining us today. I managed to catch the tail end of your panel and the discussion in there. Perhaps you could tell us what you were talking about.
Yeah, I was basically talking about genomics and the field of genomics, in its application for the individual patient, and using kidney transplantation as an example, how we move forward to help really diagnostics, hopefully therapy, and hopefully to achieve eventually individualization really of patient treatment.
Okay.
But I took a cautionary note, so I think we are making headway, but we have not reached yet that we can do for the individual patient always help. But we learned a lot about this technology, and here in Alberta, I came here because of this Genome Canada project and the microarray technology that really helped me to do this research.
Okay.
And I think we do have learned a lot, and it's fascinating, and the audience was very attentive. It's nice to see, I'm really a physician, and then to meet industry and their interests, and there is a lot of overlap. And
there seems to be, doesn't there? Yes. Yeah. And I'll just tell you too, you don't have to worry about that camera over there. Okay. It's just this one behind me that's got you. So when you're looking at something like transplants, and of course we're talking about big data here and getting all kinds of information, what are you looking at when it comes to a transplant?
My special focus also is, as you know, transplants, we need organ donors and organ transplants, and a lot of the kidneys in this case are not used because we are not sure is the quality of the kidney good and should we transplant it or not. So about 20% of the kidneys are actually not used, and that's a big problem when you think on the other hand, patients are on dialysis, they need their transplant, it's very expensive, the life quality is far better on transplant. So to find ways to assess the quality of an organ better would really make a big difference in medicine and for us. So I look with gene expression technology, so with very sophisticated technology at big data.
So when you say gene expression technology, what exactly is that?
That means basically how the genes are changed in an organ because of its quality. And the gene is basically DNA and is transcribed into a copy into the RNA. So I look at the copies, at the RNA. That gives me the idea, is there something going on in the kidney or not? And when I can look at all these 22,000 or 23,000 genes and their copies, I get a better understanding of the quality of the organ than by just looking with the microscope or by just having clinical data. So we want to integrate that, and then we can perhaps save some more kidneys, use them for transplants, and make better prediction how they will work in the long run.
So you're able to, I mean, because to me that sounds like quite a process to get the information and process it and then say yes or no. Is it a lengthy procedure, or is it as simple as looking in a microscope?
No, it's definitely more lengthy, but the amazing thing is with the technologies, when we started it took a week or so, and now it's within 2 days basically.
And how much time do you have?
It's very much a process which is machine driven. So you are not doing it your own. It's very much kind of a technical process. And the quality and the price as well has gone down so far that it's definitely within the routine reach really to be applied.
Okay. Okay, but I mean, if you've got it down to 2 days now, how much time do you have with the organ?
Okay, that's a very good point. At the moment, it's more a learning curve, so that we identify important genes, and when we have identified them, then we have a set of genes which we can measure very rapidly. So then we have a potential donor, we can look at that very rapidly within 4 or 5 hours and say, okay, this organ is good or this organ isn't that good. That's really the goal.
So the goal is to get to that. So this is not something that you can put into practice today?
No.
Okay.
Not for this purpose, really.
So when you're looking at something like that, and because there's so many genes in the body, organ, you want to narrow it down to a few.
Yeah.
Is this where the big data comes in and trying to figure out exactly what few you need to be looking at?
Exactly. I think you start with lots of data points. So we have about 55,000 data points, and we kind of really filter it down to a very small set to make it understandable as well, useful, and we know that we don't need that many, fortunately. So it might be coming up with about 10 to 15 or so genes, or even less, which help us then as biomarkers to say, okay, this is a good kidney, this is a bad kidney, or there we should do a different approach to the treatment. And we learned as well that the organs behave very similarly. It's very stereotyped, the responses, so probably we can translate that then to the liver or to the heart or to the pancreas organ. So this is a very applied research, I think, and because of that I thought there was a lot of interest from people really who are not in the medical field to say, oh, that makes really sense, and if we use a kidney transplant we save about $250,000 over 5 years instead of doing dialysis. So it's very interesting from the healthcare costs as well, not only for the patient being for life quality, which is of course the most important thing, but it has really these ramifications.
So how long do you think it'll take you then before you've gone from a week to diagnose to 2 days? How much longer do you think it'll take before you can get it to a point where you can use it?
Yeah. When I started and I showed this, the ease of implementation, and when I was, next year. But I'm now more cautious. I think these processes, they take probably 5 years or so really to be implemented then. And you have to be very cautious. You don't want to do anything wrong, that then the kidney doesn't work and you made a wrong diagnosis. You want to be very robust. And we learned really that it's not only one technology, it's really the integration of how the information from the patient, the information from pathology, the information from imaging, from all these different technologies to put together. And then I think we will achieve a better service to the patient and a better individualization.
When you look at the information, because you're obviously looking at the biology of it and checking that out, do these numbers, I guess, are you kind of reluctant to use these numbers at first? Because I mean, doctors are used to making diagnosis, and that sort of thing. Are you reluctant to use this type of research and information at first, or do you find the industry is?
I don't think they are really reluctant. I'm surprised how open they are, because everybody knows that there is deficiencies in the diagnostic systems, and we do our best, but we know that we do not really are very good in quantifying the level of sickness, for example, the level of wellness. So to have this continuity in changes or so, this I think needs better diagnostic methods. And the pathology has its deficiencies, and there is a lot of bias. The one sees these cells, the other sees these cells. How to standardize that? And with these big technologies, I think we have better objective measures to have a standardized method of analysis, so that it's independent whether it's done here or it's in Calgary or in Vancouver, they get the same result with the machine reading, and then we can compare these results as well. And that is obviously for the industry very interesting as well, to have a very objective method, standardized method, which can be used then at different places.
Absolutely. We're going to take a quick break, and we'll be back in a moment from the conference taking place here at West Edmonton Mall. Of course, it's the Analytics and Big Data Conference. Don't go away.
Business happens fast. Clients expect immediate responses. A great way to build rapport? A custom rapid video response using Skype. The Fuse Logic Rapid Video Response program will immediately separate your business from your competition. Here's how it works. Step 1. Identify a marketing message you want to share. Step 2. Contact Fuse Logic. We will help you pull together your rapid video response script with key messaging. Next, our Fuse Logic TV team will do a test call with you to check your Skype account, sound and lighting in your office. We schedule a recording date and time and produce your rapid video response video show. Here's an example.
Hi, this is Rob Pendy of June Warren Nichols Energy Group. I'm here to announce a new partner.
Don't wait. Call Fuse Logic TV today and create your cost-effective rapid video response.
Welcome back to the Analytics, Big Data, and the Cloud Conference taking place at Fantasyland Hotel this week, Monday, Tuesday, and Wednesday. We're chatting with Dr. Thomas Mueller, who is from the University of Alberta, and you said you actually came to Edmonton because of the opportunities you're afforded at the university.
No, I think Alberta was unique, or Genome Canada, we had this Genome Canada enterprise. Dr. Halloran attracted the money, the funding, and it was a big project, and I was in Boston at that time, and that was really the reason to be recruited here to work in this project. And it was 2004, so you see it's already more than 5 years that we work on this, but I think we did quite make some headway.
Is the whole research process, through the information that you're able to gather now and process it much faster, is it speeding up considerably, do you feel?
Yeah, no, I think the methods are more robust. the bioinformatics, which we had to learn really, the techniques to analyze these data have definitely evolved a lot. It's very much a multidiscipline approach. The single like me or so, I'm only one small part in this whole project, so we need really the interaction with people from economics, with people from mathematics, from statistics, from pathology. So it's a very multidisciplinary approach, and we had to learn this, to speak the different languages and to learn the same language.
Yeah.
But I think we made definitely progress.
Because you're right, because at one time everybody would likely have just been focusing on their own area, but you bring the mathematician in and that sort of thing, and all of this. Economics, of course, is important because somebody has to pay the bills. You know, you probably had to deal with them more than you liked in the past. But so you're gathering all this information. Is the information that doctors have had, because medicine is both an art and a science, and you know, the data may not have, or data may not have always been there.
No, and you know, we have all these beautiful data, and there is sometimes an outlier, and we can't explain it. You know, the data speak differently, and the patient should be feeling fine, but he is not feeling fine. There is far more to it, and we spoke a little bit about epigenetics. It's not all the genes, not the genes define not everything. It's a lot of environmental factors which play a role. So we have to learn about that as well, and because of that I really speak about integration. I wouldn't say we have now the technology which is a solution to everything. But on the other hand, we see it already being implemented in the clinic. I think in tumor diagnosis or so. A breast cancer today would not be just a diagnosis with a light microscope. Now you need the genes to say what kind of form is it, what is the response to the tumor, should we do in addition to irradiation, should we do a mastectomy, should we do chemotherapy only? These kind of questions really going to serve the individual patient, I think, that needs these new technologies.
So as opposed to doing a scattered effect of treatment, now you're able to pinpoint it a little bit more. Ideally, you probably want to pinpoint it even more, I imagine.
Yeah, and we learn more from the outliers, actually, you know.
Well, explain to us what an outlier is, because I'm familiar with the book, you know, and I'm sure a lot of people are, but when you say outlier, what are you referring to?
An outlier is who has a disease and he lives, despite smoking, 95 years of age. And why doesn't he get lung cancer? That's perhaps more interesting than the person who smokes and gets with 45 years lung cancer.
Which is what we expect.
Exactly. But we learn from these outliers as well. How does the body respond? Are there exceptions to the rule? And this, I think, will be very enriching when we understand from the outliers disease processes and these disease mechanisms and how to treat them. And we have kidneys who kind of look very good. The gene transcriptome tells us that's a beautiful kidney, it should work beautifully and right away, but it didn't work right away. And then we learned, okay, this patient had an underlying inflammation which we did not detect, or the blood pressure was so low. So there are other factors which explain why this was an outlier in the genomics analysis.
Okay, that just adds more confusion to the whole process, doesn't it? I mean, eventually it'll clear it up, but to figure out why this works.
It's true. I think on the one hand, we need all this data really to capture the complexity, but I really believe strongly that eventually it has to be simple again to be applied. And I'm always amazed when we have these findings and you discuss it with the patient, how much the patient himself or herself brings to the analysis of the data. You think you're speaking about genomics and so on. They know very well what their kidney works like and what they did, why the kidney didn't work like that. So we learn a lot really in this interaction, and that's some of the beauties, I think, of this data mining, to discuss it in a way with the customer.
Or the patient, yes. Well, I mean, data mining, when you do it, you're doing it on a huge scope, and you've got the relevant information to come up with a solution. When the patient or the customer does it, they go to Google, you know, and they just get whatever they can. Sometimes it's Wikipedia, sometimes it's something more specific. What are the dangers of the patient or customer going out there and doing a little bit of data mining on their own?
I think in general, I think it's very good. You want to have the informed patient. I think I enjoy it far more when a patient has done some Googling and read about it and so on, comes with questions to it. The problem is that still you need the trust of the patient, because I think Googling or the Google data or Wikipedia, so they are not validated. There is not a rigorous process. You can put that into the public website and it's not necessarily true. And when you as a doctor then kind of discuss and have your hesitations and cautions and questions to it, that the patient trusts you in this. I think it's really the dialogue. But the information, the power of the information is beautiful, and I can only support that, to go to it.
Right.
But take it with a grain of salt and give the doctor a benefit of the doubt sometimes.
Okay. So you're coming to the table with information. It may not be accurate, but it may help lead to questions. It can help clarify things.
Definitely.
Is what you're looking at. When you're looking at this type of, I guess, research that you're doing, any concerns out there at all that if you're able to pinpoint things that we may now, exclude people because of certain genes in their body and just go, well, that person's not, not right, so we're going to get rid of that person, or perhaps not save that person?
Yeah, no, I think it's with each new technology, there are anxieties and fears associated with it, that you get predicted as someone who is prone to aggression, or you have some genetic disorder or so. How can we keep that confidential? One thing I think I learned is really that we should not over-expect what the genes determine. There is so much more going on. So we can't say this is the gene profile for this and this disease, and this patient 100% will get it. That's very, 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 very rare. So in general, there is always variability in it. Mm-hmm. It gives us perhaps some way to say, okay, you should eat this way, or you should do this more exercise, and so you are perhaps prone to this, but it's only likelihoods. It's never 100%. Mm-hmm. So one has to really question the power of the genetics and the genomics a little bit and not overestimate it. Mm-hmm. It's not the crystal ball.
Okay, and when you're looking at these sorts of things, and you said you would hope that you would come to your conclusions within a year, and it's taking a little bit longer, and so you don't put a definite end on it. But when you're done, then it's up to the government to approve a procedure or a government agency. Is that process gaining any speed in keeping up with the times?
Yeah, no, we spoke about that in our, like the FDA approval or Health Canada approval has really accelerated a lot. These new technologies, the patenting process, the biomarker processes have definitely improved. So I think there's a lot of openness from both sides because it's so important. We have all this beautiful data, we have to use them, and we have to bring them to the patient, to the taxpayer. So I'm very positive about that. I don't think that that is the holding up of the process. When we see it really makes a meaningful difference to the patient, I do see that it's implemented in the routine care. But we have to be cautious. We don't want to bring a new technology on the market without feeling that it's really very robust and knowing the pros and cons of it.
Well, because that might be one of the concerns that people would have is, say it would take 10 years to approve something in the past, now it's approved in 1.
Yeah.
And some people may be looking at it going, well, who's pushing this through? So it's going to have to be a mindset change as well, I imagine.
That's true. But in addition, that one doesn't overestimate the technology. You have a new technology, but there are exceptions, there are outliers, and I think giving this question to the new technology and saying it's not 100% makes it easier to approve it. Mm-hmm. We don't say it's 100% correct. So I think with this iterative approach and being really a little bit questioning, it makes it easier to approve these new technologies and learn from them.
Mm-hmm. When you look at all the data, I keep saying data, you guys keep saying data, so I'm trying to get it straight. But when you look at all the data that's gathered, do you see, because obviously if you can transplant an organ and you say it can go from the kidney to perhaps the heart, the lungs, that sort of thing, we're going to be living longer? I mean, we're already living longer, but do you see that through medical technology that you will extend the lifespan of the average person as well, even?
Yeah, no, I think I'm kind of a doctor for chronic patients like chronic kidney disease on dialysis, and you know that the life expectancy changes with a functioning kidney transplant. So you know that the life will be longer. Mm-hmm. And the organ life and the regenerative and repair capacity of the organs is immense. So when you don't have a disease process going on, these organs give you really additional life years. Mm-hmm. And not only life years, I think we have now this concept of quality, life year quality. Mm-hmm. So I think the quality in life definitely is extended. And due to that, we learned that we do not have to be too limited in using organs, perhaps even from a 60 or 70-year-old donor. Mm-hmm. These organs can very well add life to a recipient. Mm-hmm. And we transplant older patients and we get organs from older patients, even from living donors.
Is that something that you've got to change the mindset there, thinking that a 70-year-old might be a good donor as opposed to a 30-year-old?
I think we do have to. We do have to make more the message that even a 70-year-old can be a very good donor.
Well, today's 70-year-old is not the 70-year-old of the 50s.
Exactly. And that's a little bit what my research tries to find, more the biological age. You know, we have the calendaric age, our date.
Right.
But that doesn't mean, I think we have the very healthy 70-year-old and the very sick 50-year-old perhaps. So I think there we need better markers than just the birth date. And one of these might be this gene expression in the organ.
Okay, Thomas, thank you very much for
You're
joining
welcome.
us today.
Thanks.
We've been chatting with Dr. Thomas Mueller from the University of Alberta.